Hello everyone, my name is Edward Marinov, and today I'll be going through the work solution for the dice game. So the question reads, a dice game is played whereby a die is rolled, and it costs $1 to play. If the player rolls a 6, they receive a return of $6, which is actually $5 as it costs $1 to play. If the player rolls a 1, they get the $1 cost of the game back, and any other number means they lose $1. Use a long run proportion to calculate whether the player can expect to win or lose money. Okay, so obviously there's a variety of programs you can use to, simulate this, but I've just chosen to use Excel. And the first thing I've done is to simulate the rolling of the dice. I've just used the basic rand between function for numbers 1 through to 6. Okay, this is just a count of all the simulated rolls within that column, which is 1,000, and that's obviously my sample size for this simulation. Okay, so our actual frequency of rolls, again, is just a count of all the simulated rolls in that column, okay, for each individual face value. And the expected frequency is simply the probability of rolling each face value, which is obviously 1 over 6 multiplied by the sample size of 1,000. Okay, and just going back to the question, it doesn't actually stipulate what sample size they want us to use. So obviously each student is going to use a different sample size. So I'd expect some kind of justification as to why they used whatever sample size they used. The justification I'd expect is something like a variance, which is the actual frequency minus the expected frequency divided by sample size multiplied by 100. Okay, and the variance you'd use is obviously whichever face value has the biggest difference between the expected and the actual frequencies. And in this case, it is for face value of 1. Okay, so the actual frequency is 176 and the expected is 167. Okay, and that's what I have here in the calculations. And calculating that, you get a variance which is slightly under 1%, but we'll just say it's approximately equal to 1%. Okay, and I'd expect some kind of worded response just to justify the variance as well. So the difference between the actual frequency and expected frequency was greatest for face value of 1. And since the calculated variance in frequency was approximately 1%, we can feel confident that the chosen sample size of 1,000 is sufficient for this simulation. Yeah, so something along those lines is okay. So moving on, we have our long run proportion, which is just our actual frequency divided by our total number of rolls. Okay, and from there we use I've used the net profit. You can obviously use your gross profit as well, but there is less steps involved when using net profit. So just going back to the question, so if a player rolls a 6, they receive $6, but they actually win $5 because it costs $1 to play. Okay, so that's $5 there. If a player rolls a 1, they get $1 cost of the game back. So they're not actually winning anything since they're paying $1 to play. So your net profit is actually 0 for that. Okay, and any other number means they lose $1. Okay, so from face values 2 to 5, it's actually going to be a -1 for net profit. And then your overall profit is just simply your long run proportion multiplied by your net profit per roll. Okay, and then at the end here, I just have a summation of all the overall net profits. Okay, and that gives us a total of 14 cents. Okay, so as I was saying, you can use your gross profit as well. The only thing is, at the end, you're going to have to take away the cost of playing the game, which is obviously $1. And that'll actually give the same answer as the overall net profit here, as you can see. So either way is fine. So once you've found once the students found the solution here, I expect some kind of worded response just to, I guess, translate what number they've found here, and I guess just to formally answer the question that's been asked. So the worded response I've provided is using a sample size of 1,000 rolls. A long run proportion analysis indicates that a player can expect to win approximately 14 cents every time they roll the die.